1D Newton's second law problem. If you're stuck, please talk to your neighbor. If your neighbor's not stuck, ask them what they're doing. You should either be writing or talking. No, that's okay. We need to start from a statement of Newton's second law for one dimension, and then it'll be a differential equation, and we need to start integrating it. Okay, well, let's go ahead and start working. We gave you some time to write down last time too, but we need working right now. You can always look through the Panopto video and refer to this if you want to write it down later. We are working it right now. Leave a spot to write it down and come back to that later. Your notes from last time. This is it. Do you have the rest of your notes from last time? You should probably sit closer to somebody so you can talk and at least see what they're doing. Why don't you two talk for a moment, please? Could I have you two touch base on strategy for a moment, please? You two are going to talk for a moment, all right? And Jeremiah, I'm going to have you join this group here and talk for a moment about strategy. So take a moment right now, no matter where you are, just take a break where you are and explain what you're doing and what your strategy is for the problem with your neighbors. Everybody should share something, even if it's...
So, did you guys figure it out, or you guys can?
I'm kind of working on it, really. Yeah.
Because I was thinking that it's momentum, one's going that way. So with net momentum, it should be, the one half is greater, so it would be minus. And then it should be like a minus equation and differentiate. Awesome. we negate it, it wouldn't be negated because then this one would be stronger. So even if we differentiate, if we were to do this half, like, do differentiate this part from this part, but then that's not really, I guess.
Yeah, but once force increases, once this decreases or something, it's the life that it has.
I get you there.
So it's still going to be like the sum of the forces over time.
I get you, that makes sense.
All right, I'm gonna give you guys just a couple more minutes to work on it, and then I'm going to work. That's very nice. Three-by diagrams is the easiest place to start, and then right up in the second law.
I started getting I get what you're saying. So you did it from the circle and then that first.
Okay. All right, I'm gonna give you another minute. I'll come check it out next. Are you in the same place, Russ?
That makes sense. I thought these are the ones I was doing. I was trying to do it. Flipping it.
That's fine. You don't always have a one-dimensional problem, as long as you got. The nice thing about the three-die diagram is that it does define the sign
Then it's
convention.
kind of just
Yeah,
easy.
that's fine.
That makes sense. Any facility to do it.
All right. One more moment, and then I'll get going. I just want to make sure that you're all at either a place where you see the way or that you're really good and stuck at a dead end before I begin to work. One or the other. You're still working, and I'm not going to start. What's that stuff there? Okay, that's fine. I thought it might be the normal course. All right. Where are you right now?
Is that not?
Yeah, that is it, and then we need to just make our substitutions for these forces, yeah. All right. So I'm going to go ahead and start working. What we are going to do is we are going to apply what I sort of modeled for you in lecture last time. I don't have those lecture notes, but I do have my handwritten notes. Where we did a problem in which we were using Newton's second law. And for the one-dimensional case, it simply still started with Newton's second law, but we noticed that we solved it and we got this differential equation, which we solved by integrating both sides multiple times, however many times we needed to get the variable that we're interested in. In the case that we did last time, it was just some constant force along the x direction, and it wound up looking like, I did my first integral here, which was a bit trivial. This one won't be. And then when I got an expression for my velocity as a function of time, I integrated that to get location as a function of time. So made the substitution there and did an integral. All right, that's the exact same strategy that we're doing today. All right, so let's go ahead and solve the problem. I've got an automobile. I've got two forces on it. So I've got Goliath is pushing the forward. So here's Goliath. And then here is David pushing like so. All right. So I've got a free body diagram here. So I represent my object, which I will approximate as a point particle. So it's a particle of mass m. And I'll draw my two forces on there. I've got the force from Goliath. He's pushing in the positive direction. And I've got my force from David here. And by the way, I should note that in this figure, I'm going to use the coordinate system that all these forces and all the resulting motion remains in the x-axis. All right, are there any questions so far? Okay. So now I need to apply Newton's second law for one dimension, which is the net of all x component of forces is equal to the mass of my object times the x component of acceleration. That results Newton's second law. All right. And just to put this into Taylor's notation, he would write this as F is equal to m x dot dot. Because the x component of acceleration, rectangular coordinates, is just x dot dot. Are there any questions about that? Okay. So now I'm ready. I'm going to flip this just for grins because I want to be able to plug in. My force will be the longer term. I want it on the right-hand side. So I'm going to have m x dot dot is equal to the net force. Well, the net force here, I need the net x component of force. So I'm going to have Goliath's force minus David's force. You guys agree with that? Okay. So I need to make that substitution. I'll go ahead and write it out in symbols first. All right. Now, both of these forces depend on time. They don't depend on location, which is a little bit friendly to start with. But they do depend on time. So now I'm ready to plug in for these forces' magnitudes in terms of time. So for Goliath, I have this constant value of F naught, some fixed value, times e to the minus t over tau, where tau is a time constant for that force. That means it's the time it takes for that force to drop to 2.73th of its value at any time. This amount of time later, it'll be approximately 1/3 of what it was before. So this is an exponentially declining force because they get tired. All right. And for David's force, I have, well, he's weaker. So his initial force is half of Goliath's, but he has more endurance, meaning his time constant for that drop-off is longer. For that drop-off by about a factor of 1/3 is longer. So e to the minus t over 2 tau. So this guy's force doesn't drop to 1.273, 1 over 2.73 of its initial value for twice as long as this guy's. You guys understand what those time constants mean? All right. And the time constants are the same for each, and that F naught value is the same for each, and I want my answer in terms of those variables. Okay. All right. So this is my expression that I got from Newton's second law. Now, this is just a differential equation, all right? So now I need to solve my differential equation. Again, I modeled that last time. So what we need to do is we need to get x dot all alone on one side of the equal sign. Just by dividing both sides by m. Now I'm done. I mean, in terms of physics, it's over. Now I am doing math. It's still math that you learned in your physics class, but it's just math now. Now I just need to solve for x as a function of time and consider the limit where time goes to infinity, what the value of x would be for that solution. Are you guys following that? Okay. Do you want a moment to try to solve this on your own? That's a real question, and I'd like a real answer. Do you guys want a moment to work on that? Yeah? All right. Do it. You integrate both sides. When I come around, I expect to see an integral sign somewhere. And you're integrating with respect to time, from 0 to some later time t. Yes, sir. Well, I don't think, I mean, it might be right, but your notation, is this where it starts? Ah, okay, good. All right. So you've got that's what I got. Yeah, that's what I got. So you've got down to that. All right, so you've already solved it. Make sure that your partner is also on the same track. Very nice. Notice, or let me remind you, because it's not up on the board right now, it did start from rest. And let's call its initial location x equals 0. That would be a good choice of coordinate system. All right. Yeah. 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 That's all that's what I need. Everybody's got what I need. That is so good. All right. So you keep working if you're in good shape. I'm going to go ahead and start working. So I need to integrate both sides with respect to time from 0 to t. I'm just going to go ahead and do it this way. Oops. All right, that's what I'm doing. And I know what I'll get on this side will be x dot minus x dot initial. And x dot initial is the initial x component of velocity, which I was told it started from rest, so I know that one's 0. Okay? Is everybody okay with what happened on the left-hand side here? Okay, cool. All right, so now I have to do the right-hand side. I'm going to pull my f naught over m out front, and I've got my integral from 0 to t. I'm going to make this to, we'll see what I do. E to the minus t over tau minus 1/2 e to the minus t over 2 tau. And then I need a dt over here. But you know what I'm going to do, because this dt should be applying to both of them. All right, I won't skip any steps. I will not skip any math steps at all. That's my first step. Are you guys okay with that step? Sweet. So now I've got x naught, and notice, or x dot, but you notice x dot will also be a function of time. That's implicit. And now I'm going to note that when I have an integral of a sum or difference, that's equal to the sum or difference of the two integrals. So I've got times the quantity, the integral from 0 to t, e to the minus t over tau dt, minus 1/2 the integral 0 to t, e to the minus t over 2 tau dt. Is everybody okay with that step? Are you all right with that? All right. Cool. So now I have an e to the u du. At least I'd like to have e to the u du. So now I'm referring to the stuff that you know from hopefully Calc 1 or Calc 2. However, the whole point of today is that y'all are probably, I expect you to be tremendously rusty. So I'm just banging you with a hammer to try to get the rust to fall off, right? Do you recognize that's what's happening here? Okay. So the hammer continues. All right. So I've got an e to the u du, except this isn't du, because if u is t over tau, then du would be dt over tau. So I need to divide this by tau, in which case I've got e to the minus u du. Are you guys all right with that? It only works if I put a tau out front. All right? Are you guys okay with that step? Rodney, are you okay with that step? Okay. Same thing happens here. I want to have e to the minus u du because I know how to do that integral. If my u is t over 2 tau, then my du is dt over 2 tau. So I put a 2 tau down here, and I can only do that by putting a 2 tau out front. Okay, cool. Now I have an integral I know how to do in both cases. So my first term is f naught tau over m. And e to the u du is kind of nice for giving us e to the u. And I've got to do it. I do have to do the minus sign, don't I? Yeah, I've got to do the minus sign. So I will put a minus sign here and a minus sign out front. Sorry, it's getting so crowded. Minus tau. All right, so then I get e to the u. So e to the minus t over tau, which I have to evaluate from 0 to t. All right, and then I've got, again here, e to the u du. I'm going to put a minus sign there. That'll make that into a plus sign. I multiplied in here by a minus sign, so I had to multiply out front by a minus sign, which turned the front into a plus sign. Okay, so I know for this integral, I'm going to get plus tau times e to the minus t over 2 tau, which I have to evaluate from 0 to t. Is everybody all right with that? Are there any errors up there right now? Okay. I make errors all the time. You guys who don't know me, I make errors all the time. It's my jam. All right. So let's go ahead and move on. So what have I got here? I've got, see, here's one right here. I pulled my tau out front, and then I left my taus in there. See that error right there? That was fun. Okay, now is it, I think it's all right. Now I can pull my tau out front. I'm obviously wanting to do that. F naught tau over m times negative e to the minus t over tau. Oh, this is complicated with that minus sign in there. Minus 1, how's that? I'll just evaluate that function and put my minus sign out front. Because when t is 0, I have e to the 0, and that's 1. You guys all right with that line? Okay. So then I've got plus tau times e to the minus t over 2 tau minus 1. Got to change that front one to a curly bracket because I use the square brackets later. All right. So
Do you need that one?
I don't need that second tau now. Thank you. All right. So let's go ahead then and keep working. All right. So again, in the interest of being very clear, I'll do every single step. F naught tau over m. I've got negative e to the minus t over tau plus 1 plus e to the minus t over 2 tau minus 1. So I'll just go ahead and note that I've got a plus 1 and a minus 1 here to keep it involved, and those two are going to cancel each other out. And that's my expression for x dot as a function of time, or velocity as a function of time. If I had asked you what's its velocity as t goes to infinity, what would you say? 0, right? What's the velocity of the car as t goes to infinity? Look at that and tell me the answer. 0. When you plug in infinity, again, I'm not a math professor, I can say that. You plug in infinity for t, you get 0, right? So I know that this car is eventually going to come to rest somewhere. Where is that going to be? All right? Yeah. We need to have more fun. All right. How about if I let y'all loose on the next integration for a couple of minutes? And then I'll show you. But I'd like for you to try on your own first. This is a skill that takes a lot of practice, and it's not something you get right the first time, and that's all right. Well, you kind of do, because that'll be x as a function of time minus x naught. But if we want to call x initial 0 as a choice coordinate system, that's fine. So then you're ready to do those. All right, so I'm going to go ahead. You guys can keep working if you're not stuck. I'm going to go ahead and start working. I've got to integrate both sides again from 0 to t dt. All right, and on the left-hand side, I'll get x, which I have to evaluate from 0 to t, so that'll give me x at value t minus x naught. Again, I'm going to make a choice of coordinate system right here, actually. How about we do it there? You can't even see where I'm writing. I'm going to note that I'm going to let x naught be 0. That'll be my coordinate system, okay? All right. So I'm going to let that guy be 0. It'd be fine if you had it in terms of x naught, though. That's fine, too. All right, and so I've got this constant I'm going to pull out front of my integral, f naught tau over m. And make a curly bracket here. I've got an integral from 0 to t of negative e to the minus t over tau dt plus an integral from 0 to t of e to the minus t over 2 tau dt, and curly bracket. Are you guys all right with that? Is that so far so good? Okay, so now I want to evaluate the first integral. I need e to the u du. What is u? Negative t over tau. So what is du? Negative dt over tau. So I've got dt over tau. I can take care of that. Divide by tau there. And I have to multiply by tau up front, and everything's fine. All right? And then I already have a minus sign in that term, so I'm going to take that minus sign and put it into what's called the Jacobian. Do you guys know what a Jacobian is? It's your du. Whatever you've chosen to use a more complicated variable than your simple variable, the Jacobian is like such as u. The Jacobian is du. It's the thing that you have to multiply by in order to do it, get a simple integral. Okay. Similarly here, my u is negative t over 2 tau, where tau is just a constant. So therefore, du will be negative dt over 2 tau. So in order to get over 2 tau, I have to multiply out front by 2 tau for my equality to hold. And in order to have my Jacobian correct, I have to have a minus sign there because my u is a negative function. Okay, so now both of these integrals are in the form of e to the u du. So now it's just a matter of writing the indefinite interval and evaluating from 0 to t. All right, so I've got f naught tau over m times, I'm going to make this tau squared if I can remember to do that. I'll take that one of those taus out front. So I've got times e to the minus t over tau, which I'll evaluate from 0 to t. This will give me x as a function of time ultimately, and then I'll take my limit where t goes to infinity as the last step, okay? And then I've got plus 2 times the integral I did here, so that'll be an e to the minus t over 2 tau that I have to evaluate from 0 to t. All right, more mathity math. And I've got x as a function of time is equal to f naught tau squared over m times e to the minus t over tau minus 1 for my first term. You guys all right with that? Plus 2 e to the minus t over 2 tau minus 1. Why do I feel like there's a sign error there? There is a sign error there. I put a minus sign there and I didn't put a minus sign there. Is that correct? There had to be a minus sign there. All right. Welcome to Mechanics by Stoddard. There will be sign errors. I apologize though. Okay. Are you guys all right with the fact that I made a sign error here? I had this guy here. I put him here. I made his Jacobian. I made it negative, and I needed to put a minus sign up front. Rodney, do you see it?
Oh, yeah.
There.
Just looking at something else.
Okay. Are we okay? Has the error been made clear? Yeah? All right. Okay. Minus 1. Okay. So, what I have here is f naught tau squared over m. I've got a negative 1 plus 2, so that's 1, plus e to the minus t over tau, minus 2 e to the minus t over 2 tau. That's my function for location as a function of time. Are you guys all right with that? So now, as soon as they started this push of war contest, I know exactly where that car's center of mass is as a function of time forever. All right? Where is it located when time goes to infinity? Where does it wind up when it stops moving? Let me check and make sure I got the answer right. Did I get the right answer, by the way? Okay, all right. All right, so where does it wind up when t goes to infinity? What's the value?
F naught t squared.
F naught tau squared over m. This is x, we can call it x final. I mean, just implied by when t goes to infinity. And we're done. Okay, so this has been the day that I've been looking forward to since the first day I met you. Because you know I've been dying to be like, these forces don't have to be constant. You can still solve Newton's second law for motion, right? You guys remember me saying that? I really want to show you how to do it. It's really, we're 2 days into class and we can do this now, all right? Are you guys all right with that? So hopefully you see what Newton's second law can do is if you know forces, even if they're functions of time, even if they're non-constant, later on, even if they're functions of location, you can still evaluate the forces and find the motion of the particle in which those forces act as a function of time. Meaning at all times you know its velocity, you know its location. And like, that's what it's all about. All right? That's what Newtonian mechanics, that's at the heart of Newtonian mechanics. This is what Newton could do in the 1600s. All right. And we can do it now, so that's good. All right. So that was intended to be like a little bit of a jarring experience, or at least a look what you can do experience for yourself, that you can show yourself what you can now do with Newton's second law, if you're willing to do differential equations, meaning solve for x double dot by integrating twice. All right? Are we okay with that series of steps that we took here? Okay. But how about this, if I'm a little bit more concrete about that? Let me remind you of the series of steps that I took here. I drew a picture. Within my picture, I created a coordinate system. Within that coordinate system, I broke my forces into components and found the net component for each direction. In this case, it's just the x is the only one that's non-zero. There's also a free body diagram here, because as I evaluate Newton's second law, in order to find the net component, I need to be able to have a sign convention that I can easily look at. All right? So these things are still expected in every single Newtonian mechanics problem. There will be a drawing of the situation. There will be a free body diagram from which you take your components to find your net force for Newton's second law. Okay? Because this right here, as your author points out, was the trickiest part of all of introductory physics, and we're not skipping it now, we're using it now. Right? Okay. And once you have Newton's second law written out in terms of x components, once you're able to find values for those components, then you're to the point that you just are doing math after that. The physics is over. All right? Okay. But we're still going to show our steps such that someone, say our supervisor someday when we work at our engineering firm or for the government or wherever it is that you work, although even though you're a physicist, your title will probably be engineer or scientist, someone else in your research group has to be able to present your work as in a group setting, and that it would go well enough that you've shown enough there. Okay? All right. And we always do box our final answer. All right, so those things are still expected. And that one more thing that was expected was that when I used a law or definition, I named it. In this case, I only used Newton's second law, but I did name it upon its use. Are there any other questions? I mean, in terms of, why am I saying other questions? Have I made myself clear to you guys about the steps that are going to be there for me to follow? Okay. All right. So let's move on. All right. So let's talk about conservation of momentum. All right, so again, I wanted to show you something a little bit exciting, but we still have to go back to sort of some, are you kidding me? is it 1:44? I have 6. Did that take like the whole hour? That was still a good hour, I hope.
Yeah.
Okay. All right. Anyway, so conservation of momentum. Conservation of momentum is, in some ways, it's a statement of Newton's third law, in terms of, that's how Newtonian mechanics states it. But we'll see it's actually something more general than that as well. All right. So I think your author does a nice job with this, so I'm going to steal his argument and use it forever and ever from here on out. So like, you know, if you chose to push against a wall like so, like it's supposed to look like their legs are close together, clearly you're pushing against the wall. You can feel that in your palms, but also the wall must be pushing back against you, or else you would be falling down standing like this, unless something was pushing back against you, right? Because you've got your net force here, your weight force here, you've got your upward force here, your normal force, and you would be angularly accelerating, right? If it weren't for that wall. All right, so clearly there must be a force pair here, so that I have a force that is on the wall by the person. So we will write that like this. So it's the force on the wall by the person, and this will be the notation that your author uses. So it's on wall by person. And that's what the two subscripts mean. On the first subscript by the second subscript. Similarly, back here on this person's hands, there is a backward force on the person by the wall. That's the force that's keeping them from falling forward. Okay? All right. So this is the force on the person by the wall. Newton's third states, if object 1 exerts a force on object 2, then object 2 always exerts an equal and opposite force on object 1. And by the way, your author is going to call that force exerted by object 1, he'll call it the force on object 2 by object 1. So it exerts that force on object 2. So again, notice the notation. On object 2 by object 1. Oh, I'm off the page, I apologize. If object 1 exerts a force on object 2, we would call that force F21. Then object 2 exerts an equal and opposite force on object 1. We call that force F12. Such that, this statement also could be restated as F21 is equal to minus F12. Forces always come in equal and opposite pairs. And because of this, forces always have to be by something and on something. All right? All forces, you should be able to evaluate what is doing that force and what is it doing it on. Okay, now I do need to make the official homework announcement at this time. So a week from today, we will have homework set number 1 due. It consists of problems from chapter 1. And they are 8, 10, 18, 30, and 37. All right? And so I think that we actually got a lot done today, even though it feels like I maybe spent too much time having fun. But I think that was useful. So we will still finish the material in this chapter next time. It's a little bit later than I anticipated. But I moved the fun stuff up, and so that's why it happened. All right, are there any questions for me? Have a great day. I'll see you Wednesday. Everybody come Wednesday. I can't handle this attrition. I need you all here. And find everybody who's not here and bring them along. All right. Thank you.
Yeah, we have at 7 a.m. anymore, so.
That's